Hello, my name is Brian DeLuryea, and this is my Physics 2212 Lab 4 DC and RC circuits. So, an introduction to this lab, some of the objectives are to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. Some of the important topics that we'll be using are Kirchhoff's loop rule, node rule, Ohm's law, and capacitance formula. So these equations and concepts, loop rule is just that the sum of all potential differences around a loop has to be equal to 0. Node rule is similar in that the sum of the currents flowing into a node in an electric circuit must equal the sum of the currents flowing out. Ohm's law is that the voltage drop across a resistor is proportional to the current flowing through it, and its resistance is equal to delta V is equal to IR. And capacitance is C is equal to Q over delta V, or that delta V is equal to Q over C. Resistor equivalence for series is just that the R total is equal to R1 plus R2 plus etc. Whereas in a parallel circuit, 1 over the R total is equal to 1 over R1 plus 1 over R2 plus etc. Part 1, charge conservation and energy conservation in series circuits. So the first step was to predict the currents in I1 and I2 as measured by the two ammeters. And since these are in series, the current will be the same. So I is equal to delta V over R total. And after some manipulation, you get that the current's equal to 0.02 amps. Once we simulated this in CCK, we see that the ammeters do in fact read 0.02 amps, and therefore our experimental value matched the theoretical value. And I also tested this when one of the ammeters is reversed, and it still reads 0.02 amps. When one of the ammeters is replaced with a voltmeter, the voltmeter reads 3 volts because it only reads potential difference across the battery, and therefore delta V is not equal to 0V because loop is not completed. However, the ammeter reads 0 amps for a similar reason because the circuit is open. So the voltage different across the circuit. So the sum of the individual potential differences for a round trip around the circuit should be equal to 0 volts. So the measured difference is 3 volts minus 0.959 minus 2.041 is equal to 0. The ammeter reading doesn't change after the voltmeter is attached in parallel. Voltmeters have infinite resistance, so no current is going to pass through it, and therefore the ammeter reading doesn't change. All right, adding an ammeter in parallel. So the current on both ammeters now reads 0.06 amps instead of 0.02 amps. Because the current is split between the ammeter and 100 ohm resistor, all the current will go to the ammeter since it has 0 resistance, and therefore the only resistor in this circuit is the 47 ohms, and therefore you get a current of 0.06 amps. The resistance of each circuit element that I calculated, you can just follow this here. Basically, R of the 47 is equal to 47.95, and R of 100 is equal to 102.05. Oh, and also the wire and ammeter both have a theoretical value of 0 ohms. RC circuits. So first step was to connect a battery to a 10 ohm resistive bulb and a capacitor in series. And the light bulb will start off bright as current flows at a maximum. As T increases, the bulb dims and the current decreases as charge builds on the capacitor. And when T is much greater than 0, the capacitor has been fully charged and the bulb no longer shines, and the current is 0 amps. When we discharge the capacitor, the light bulb starts off bright as the current flows in the reverse direction. As T increases, the bulb dims and current decreases as the capacitor discharges. And after a long period of time, the capacitor is fully discharged, the bulb is off, and the current is 0 amps. The time for the capacitor to charge and discharge using 10 ohm and 20 ohm bulbs is shown here. Essentially, since the resistance is twice as great, the time to charge or discharge will also be twice as great. The voltage across discharging capacitor over time. So these are the 4 steps that we had to take. We simulated a circuit in CCK with a 9-volt battery, 200 capacitor, and 30 ohm light bulb. We had to measure the voltage across the capacitor with the voltmeter. We had to set the capacitor to discharge and then plot 20 seconds of delta V versus T data on an ln of delta V over delta V initial versus T plot. To estimate the RC value graphically, I followed all the steps shown below. And so the theoretical value for RC was 6 seconds. And after all of the calculations were done, the RC was 6.906 seconds. This is a 15% error, so it is relatively close to the theoretical value. In conclusion, what if you were doing this lab in real life and used an actual ammeter instead of an ideally simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So a real ammeter would not have zero resistance, and therefore the overall current reading in the circuit would be lower than the ideal value predicted. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? So the EMF plus delta voltage equals zero means that the only voltage drop occurs on the capacitor. Therefore, the capacitor would be charged immediately upon connection. However, in real life, since the wires still have some resistance, it would take almost zero time to charge the capacitor, but not exactly zero. Thank you for watching.